USD, well, I'm starting the introduction, or during the lecture you can browse through the book, just entertain yourself, pass them across if you want. So we are going forward in our course, and there will be little administrative introduction to remember what we should do, what we have done, and then we will continue the scientific part for describing electronic structure. So there is no handouts today, but please pass the book and just browse them, and if you want to check them out for EDU2, this will be okay. Maybe more handouts later. I did compose a little homework which will be based on today's lecture. 7 minutes. Also, if you feel that you are late with some previous homework, do not wait, like, oh, I should concentrate my forces and do all previous. If you feel that this one is easier, do it right away. They are not connected and they are not built one on the top of each other. If you feel that you are more comfortable with one, do the one you are comfortable with.
Excuse me, Dr. Gillian.
Yes.
Can you adjust your mic position? I'm having trouble hearing you.
Okay, thank you. Is it better now?
Yeah, it's better now.
Okay. We are going to meet. Well, it is not a obligatory part, but I invite you to meet today at the basement of Arts and Science 16B for making a little lab, and we will be covering. We will start covering the topics for another oral presentations, mastering our skills in operating Gaussian software. And one of the 3 books I'm passing today is a manual written by Gaussian producers. Right now, Mohammed is keeping them, but you can focus your attention on it. And it has most of the portions that we are going to try to present at the end of February. Okay. Yes. Yes. So scientifically, we are going to keep our path towards electronic structure methods, and our next big goal is so-called Hasselhoff method, and it will probably take 2-3 weeks. So it is a big cornerstone of the whole course. And right now, we are stepping aside for 1 or 2 lectures and just recalling what is spin. Most of you are knowing well what it is, but it is better to recall the practical side of this knowledge, because we will be using it, and it is better to be sure that we all are on the same page. And as a benefit to the whole course, this today's lecture will justify the later determinant introduced last time. Okay, so this is homework number 5. So it has strange symbols, which look maybe scary, but after sitting here for half an hour, you'll see that it takes maybe 10 seconds per each of them, or maybe 1 second, and 2 minutes here and 1 minute here. So it is just little, very little exercise. So I assure you that this is really simple. Anyone is going to enter the door? You know, So here you have a chance to have a look on our homework, but it is also available on detail. So here let me just plain open cards and share the suggestions for oral presentations. So this all is considered as extra credit. There is no obligation. You are free to choose any subject you want or not to choose. So those are just optional subjects that you may want enthusiastically present in whatever 3 weeks as mastering our skills in operating Gaussian software. So what is most beautiful here is a skill how to plot molecular orbitals. I would choose this one if I need to present. What is most helpful for practical work, if you plan to use Gaussian in your everyday work, are those 5 and 6. So there are possibilities to operate Gaussian software completely in text format. There is a chance to do all calculations avoiding Gauss view, avoiding graphical part. And sometimes if the model is really big, it is not possible to modify it by hand, or it takes software get delayed when you start to rotate it or click somewhere. So operating software by text files and analyzing the output, just looking at a text file, is a very useful practical skill. Yes, yes. Just 1, 2, 3, 4, 5. You have about 2-3 weeks before presentation, so you can. I will try to cover all of those in the lab, but then you can pick up which one you want to present, and you do not need to answer right now. You have about week or 2 weeks to select. And we will also get some helpful skill of so-called density of states and learn how to plot it using the Gaussian software. Okay. So let me quickly review where we are now. So we have reduced our molecular Schrödinger equation to only electronic part. And we do have kinetic energy of electrons, potential energy of electrons interacting with nuclei, and potential energy of electrons interacting with each other, all acting on unknown electronic wave function. And we want to solve this time-independent Schrödinger equation to find this psi function. Since psi depends on many arguments, positions of electrons, number 1, number 2, number 3, we have we've made an acquaintance with the concept of Slater determinant. So the multi-electron wave function is composed of building blocks of one electron orbitals. And they are composed by finding the determinant, arranging the orbitals in this direction, and arranging number of electrons, arranging arguments in this direction. So by now we phenomenologically postulate that this will work well, and this will match the antisymmetry of conic wave function. So where this formula is coming from? Why you should believe it? Does it make any sense? This will become clear after we focus a little bit on concept of spins of electrons. So those single electron wave functions, which are building blocks, functions are very often taken as atomic orbitals of hydrogen atom, right? And the equation for those is too complicated. Just putting it as function of one. But what is critical to put here the right indices, the quantum numbers for hydrogen atom. And I have a little question for you. How many quantum numbers are necessary to specify an orbital of hydrogen? 4. Anyone objects, or 3 or 4? Raise hands who wants 3 quantum numbers. Raise hands who want 4 quantum numbers. Okay, 4 wins. So they are principal, orbital, magnetic, and spin. And by now we were speaking about probably only 3, but we were not explicitly describing the spin quantum number. Although probably through your basic education you all know what it is. So what is spin? Anyone wants to help me? Okay, who has an idea what is spin if it would be a written work? Oh, okay, yeah, this is good. So it is some property, some observable, generically related to rotation and to angular momentum, that it can take only 2 values, rotating in one direction and corresponding to rotating one direction or another direction. So it is, we cannot say that it is rotation, but it is related. It is same dimension. So, additional quantum number, same dimension as angular momentum. And Muhammad was giving us a suggestion of rotating one way or another way, corresponding to two quantum numbers, plus h bar over 2 and minus h bar over 2. And you know the Planck constant has a dimension of angular momentum, right? So there is an additional degree of freedom. And this degree of freedom is not continuous. It has just two discrete values. Freedom. Okay. So what we are going to do is to review how this additional degree of freedom can be treated mathematically, and how the treatment of a spin degree of freedom for a single electron can be expanded to treatment of many electrons. In simplest case, 2 electrons. So those all are baby steps, and they are not mainstream of our course, but they are like auxiliary materials that help really well to percept the rest of the course. So right now we will be focusing on mathematical tools that help to treat this degree of freedom with only 2 values. Okay. So there are 2 possibilities to call them. These 2 values. There are many ways. You can call them plus and minus, or one can call them 0 and 1, or one can call them alpha and beta, or one can just show the direction, meaning that it is symbolically pointing the direction of angular momentum. And the most critical, most important thing that makes difference between I don't know how to speak. Sorry. So main difference between classical and quantum treatment is that system can coexist in several states. So we need to be able to treat this coexistence. We need to be able to describe how system converts from one spin state to another spin state, if it ever occurs in the nature. And we should think ahead whether, if there is a degree of freedom, probably there should be a term in Hamiltonian, there should be a term of energy that contributes to total energy depending on the spin. Maybe in several practical models this term is negligible or 0, but in some cases there should be additional terms in Hamiltonian that corresponds. And one example where this is really important is NMR experiments and describing those. Also, we would like to be able to mathematically answer in which state our system is, to artificially model the measurement of a spin. This is what we will be doing for the rest of the lecture. Okay, so we will follow this path by using the concept of so-called ladder operators, and this concept is common, and it is frequently used for several simple systems. It's used for harmonic oscillator. Oscillator used for angular momentum, and it is used for spin. So it is not something new scientifically, it is just a tool to treat those systems. So we are introducing the object which changes the spin. So we want to make it up if it was down, right? And we are trying to compose this object by using Dirac notation. Please raise hands so that I do not go too far if the word Dirac notation makes you uncomfortable. Do not oh, okay. Raise hands if the word Dirac notation makes you comfortable. Okay. So those angular brackets are replacing wave functions in those cases when we are too lazy to think ahead whether our variable will be continuous or discrete, and we do not want to specify how we can integrate or make a summation over this variable. It just shows the general approach that there is a wave function of some dimension or state of system of unknown dimension. And there are some general rules that can be treated without specification of the details. And what is important that usual wave function is replaced to bracket going from left to the right. The conjugated wave function is replaced to angular bracket that goes from right to the left. The integration of conjugate times usual wave function is replaced by 2 by combining those two together. And some of you know what I will be spelling or writing right now. So since this is a bracket, this is bracket, but they are merged together to build an observable or convolute. So the people split the word bracket on 2 parts and call the one that arrows to the left cat and the one that arrows to the right bra. Okay? Are you comfortable with this now, more or less? No? Yes? Okay, good. So there is a very little trick. So if one puts those bra and cat vectors in the order to form a word, bra and then cat, then it generates a number, meaning number instead of operator or instead of quantum state number. Only bra and cat vector, they correspond to quantum state or to a vector. But if we swap the order of bra and cat, then out of 2 states we compose an operator. So if you have a cat and then bra, then this will be an operator. This is a very simple very nice toy that maybe looks ugly on the first glance, but as soon as you write it once, you will not forget it for the rest of the life and you will enjoy it. So it makes many calculations much simpler. So you do not need to take integration or multiply matrices by using this notation. So here we are building an operator that flips state alpha into state beta. It makes from spin down, it makes spin up. We just put those cat and bra in the reverse order. Okay. And then we are applying this new operator that we have designed to spin state alpha. And please do not think that it is something too far from our course. Right today, when we will be looking on the Gaussian output files, you will see that it will have the keywords in the output file, alpha states, beta states. So it is related. So we are plugging in our S plus operator here, and we are just rewriting this alpha symbol here. So we do have three components, three factors here. Yep. And they are partitioned as an operator times state, right? But no one forbids us to consider them in a different order. So we can repartition them as vector times these two ra times cat. We do repartitioning. And when bra meets cat, we can call it convolution. So when bra meets cat, it generates a number. And here it generates a very simple number, either 0 or 1. So if these vectors are the same, it generates 1. If they are different, it generates 0. So we are looking here. Ra alpha times cat alpha gives 1. Therefore, the whole expression is equal to 1, just number times beta state. And we have the definition of this ladder operator. So by applying this object to this vector, we are getting another vector. So we are flipping the spin. It is a mathematical tool that helps to flip the spin. Make sense? Good. So we can design a thing that flips it back from beta to alpha, and we are going same way. Yep. Okay, so we have our arsenal. We have S plus and S minus operators. We know how they affect the quantum state. And this is a task 1 from the homework. So you apply, for example, S minus to state alpha. So you get alpha, beta, or operator. You apply it to alpha. So you repartition it as ra times cat. And you see that here the vectors are different. So you have beta times alpha. This equal to 0. Therefore the answer here will be 0. Well, if you have the s minus times beta. It will be alpha beta for the operator, okay, times beta. So we are repartitioning it as bracket, and here beta times beta, the vector coincide, so it gives 1. 1 times alpha, alpha gives alpha. So we already done half of your homework. Okay. Okay. A little exercise that looks senseless right now, but later it will bring healthy benefits. So by the quantum nature of electron, it can coexist in state up and down, which is not possible to imagine classically, meaning like the globe rotating clockwise and counterclockwise at the same time. Or there is a probability that it rotates this direction and this rotation at the same. But as a result of the measurement, we can get only one number. So how can we find the probability that this electron is in alpha state? How to extract the probability that it is in spin whatever up and down out of superpositional state? This is a maybe too silly question because we already know the answer. So if you pose the superpositional state as this coefficient c alpha times vector alpha plus c beta times vector beta, we know that alpha squared plus beta squared equals 1, and this c beta squared will give the probability that our spin is in state beta. But can we get the same result with some rigorous procedure, some very deterministic procedure that can be expanded to much more complicated cases? So here we just intuitively know the answer, but as soon as we have 2, 3, 4 electrons, it will not be possible to predict the outcome. So we need some procedure. Let me reformulate it once again. So we do have spin state, quantum state in basis of two states with two expansion coefficients. And we need such procedure that will take this vector and get this answer. Some rigorous procedure. Okay. So let's play a little mathematical toy and just check. Well, by saying so, I predominantly know what the answer, but I'm going to lead us to this answer. So let's consider subsequent application of raising and lowering operators, and then find a matrix element of it, and check whether it will be helpful in answering our question. So so operators can be applied to vector one after another, and one can apply several operators. So what if we use lowering operator first and raising operator second? and we treat them both in Dirac notation. So our lowering this was minus, this was this plus. So this long list can be probably simplified, right? We should always be alert, and as soon as we see bra and cat meeting each other in a right order, we can replace them to a number. Here the number will be 1. So this should be equal to beta times beta. Let's see what I have. Okay. Yeah. So they meet each other, they give 1, and then the subsequent multiplication of lowering and raising operators is beta times beta. So if it acts on the beta state, it will generate beta state again. If it acts on the alpha state, it will generate nothing, 0. So it is a little trick to eliminate anything that relates to alpha state. So it projects the whole state only on the beta direction. Project on beta direction. And in some textbooks, the operators that have cat and bra with the same argument in reverse order, they are often called projectors. Okay. So we are looking for rigorous procedure. We do have in our arsenal the projector, the product of lowering and raising operator. And now we are planning to inspect our quantum state. We need to apply operator. We want to take our quantum state as an argument, and then we need an answer as a number. Probability is a single number. We need an answer as a number. That the system is in state beta. We are going to get the answer C. So this is our input, and this is our output. And we need to design a procedure that will take this one, we bring it here. So the simplest possible operation used in quantum theory is taking a matrix element. Right? And for taking a matrix element, you need to have your quantum state, another quantum state, and put an operator between them. So we are going to treat this construction. So we already have this cat of our superpositional state, and here we need a bra. So the bra state means that you change the arrow here for alpha and beta, and you add the complex conjugation for coefficient. And redirect arrows. Okay. So what we are going to do, we are going to take our bra, our operator, and our cat, merge them together and see what is happening. It's very basic operation. It may take a little writing, but not too much. We are going to combine bra, operator, and then cat, and see what happens. So this is our bra. See, arrow is changing direction, and here is the conjugation signs. Here is our operator, and here is our cat. The direction. So the rest is just little practice of middle school algebra. So just opening the brackets and see what is happening. This one should be replaced to beta times beta. Then there are two terms here, and there are two terms here. 2 by 2 will be 4, right? There will be 4 terms total. Let's practice it a little. So I take this times this times this and put it as the first term. T alpha star T alpha alpha beta alpha. Am I correct? Please catch me if I'm doing something wrong. I believe that is correct, but who knows? So this alpha comes from here, this alpha comes from there, this beta times beta comes from here. And those coefficients come from here and there. And we do see predominantly that this term will contain beta times alpha, which will be equal to a number, and this number equals to what? 0, yes. And also, this is also bra times cat. And the states here are different. It will be also a number, and it will be also 0. So there will be 4 terms, and each of the terms is composed of 2 coefficients, and then a pair, 2 pairs of bra and cat, which are convoluted into numbers. And if at least one convolution gives 0, then the whole term is getting 0. In this, at least one bra convolution 0, whole term is 0. Let's inspect the rest of the terms. So we are getting second term, third term. We are replacing those by alpha and beta. Okay, so we already practiced the first term, and the rest of them will have different combinations of alpha and beta here, and different combinations of alpha and beta in the convolutions. So here, beta times beta will be 1. Yes, alpha times 0. This also 0, 0. So first terms is 0. Second term has 1, 0, so we also remove it. The third also 0, 0, 1. So 1, 0 is enough to cancel everything. And here we have beta, beta gives 1, beta, beta gives 1. And, up front we have a coefficient C star beta, C beta. So the answer is C beta star beta. So it is the answer that we wanted to get. So we should become very happy and saying that yes, our goal is achieved. So if you want to find the probability that system is in a specific state, we need to find a matrix element of projector operator with this state. So why did we spend time on this? Is there any value in this exercise? So for those cases when spin effects are not negligible, one can add additional term into Hamiltonian. There is a energy contribution, and it is often formulated in terms of those operators. So in addition to all molecular terms that we have already written, there could be terms written in this form. So it is one benefit. Another, even if the contribution to energy from spin states is negligible, they are allowed, electrons having spin are allowed to exist only in specific configurations, as we already know is written down in form of Slater determinant. And to find this specific shape in which we put together the building blocks, the single electron orbital, is coming out of the natural eigenstates of total spin operator. And total spin operator is also formulated in terms of the product of this raising and lowering operators. And practically, by considering the total spin operator for two spins for two electrons, we are going to justify later determinant. So if you were reading some other books on quantum theory, you may want to see connection between those raising and lowering operators and standard X and Y projections. They are connected. Here I would like to present a little table. So this is probably just a handout as an auxiliary material, but it will help us to feel better what the objects we are working with are. Here are the objects that we were playing today with. So those are cat and bra states, superpositional states, raising and lowering operators. And here are Dirac notation that we were using for them. And here is an alternative notation in matrix form. Since spin state or single electron, single spin has two possible values, it is two-dimensional space. Therefore, it is two-dimensional vector. So this cat vector for spin down, we were referring it as this symbol, but it is also can be related as column vector which has 1 along one direction and 0 along another direction. If you will have beta, then it will be 1, 0. In case we are having bra for the same quantum state, then it is translated onto language of vectors and matrices as two-dimensional matrix, which is row matrix instead of column. And this notation is designed in such a way that if you multiply bra by cat, you have row by column multiplication rule, and then you get a number. This all is set up. So if you do have a superposition of one basis vector times some coefficient plus another basis vector times coefficient, then you have these coefficients plugged into column vector. If it is a bra, then there are same coefficients arranged in form of row vector, and they do have a conjugation, so that if we multiply row by column, this by this, we will get normalization. We will get 1. And here are the operators. So if the quantum states are vectors, then the operators are matrices, because matrix is something that affects on the vector and converts it into another vector. So the one that converts alpha into beta can be written down as 2 by 2 matrix with only 1 here, and another one can be written down as a 2 by 2 matrix with only 1 there. And if one practices applying those, one will get same results as we were getting, but it will take a little bit more space. And if the dimensions of the space is 4-dimensional, 10-dimensional, 100-dimensional, it just will take more paper and more effort than Dirac notation. Okay, so let me summarize what we were doing and what is our map. So our goal is electronic structure. And we are going to describe it by so-called Hartree focus theory. And on our road, we have learned the concept of Slater determinant. There will be another road blocks for correlation and exchange energy, which will take time. Correlation, exchange, and mean field concept. But today we made a little bypass. So we stepped aside and proposed what is spin. Maybe we will take part of the next lecture to use the concept of spin to justify greater determinant. So everything we were doing together is not on our straight road. It was a supplemental material to help the perception of the main goal. So with this, I have completed everything I planned for today. I will happily stay here and answer your questions. Are there some? If no, then class is dismissed. And please stop by in person and ask any questions. Okay, thank you.
Sanya? Teman-teman main kau berapa lama di guide? Tapi di guide dan ini merah negara.